our first presentation. Mr. Dan Steward is currently a consulting geologist with Republic Energy operating in Dallas. He received his Bachelor of Science degree in geology from the University of Houston in 1972, and he's been involved with oil and gas industry for 46 years. During his career, he's been employed by Ames Oil and Gas, Dresser Magabar, Shale Oil Company, and Mitchell Energy. From 1981 to 2001, he was at Mitchell Energy and a member of their Barnett Shale team. During this 20-year period, he held a number of management positions within the company, and in one capacity or another was always involved in the Barnett Shale. In 2005, Mr. Stewart was asked to write a story of the evolution of the Barnett Shale play by George Mitchell, which was published in 2007. In addition to this honor, he was selected to the American Association of Petroleum Geologists as their 2007 Explorer of the Year Award for his role in the Barnett Shale and one of the largest gas fields in the United States. So with that, I'll ask Mr. Stewart to come up and tell us some of the history of how the Barnett Shale was developed by Mitchell Energy.
It's an honor to be here today. When I kind of looked through the credentials of all the folks involved, and I looked at the number of PhDs and doctors, I got a Bachelor of Science degree in geology in '72 and just barely made it. So one of the things I'm going to do today is give you the benefit of my experience. And I'm not saying that's right or wrong, but I am not preaching, okay? But one of the things that people in science and engineering and medicine, I think, understand is that there is no settling of a science issue. I don't care if there's consensus. We find that with time, science changes, and it helps us to understand what we're looking at better, and that's what happened with the Barnett Shale. George Mitchell is what I consider a visionary's visionary. I've worked around a lot of people who I consider visionaries, and he's at the top of that list. He would do things, and I would look at it, and I'd think, what the hell is this man doing? And within a year, I'd understand exactly what he was doing and feel pretty stupid for not understanding it at the time. He, I think, single-handedly, with the help of others, but he put the puzzle together on the Barnett and made the Barnett work. And he started assembling that puzzle in the 1950s. In the early 50s, George went out and found what looked to be a very significant stratigraphic play in the Fort Worth Basin. This is the outline of Fort Worth Basin. And he went in with some other folks, drilled some wells in the Wise County area, and as a result, identified quite a bit of gas in an area that was controlled by Lone Star, and Lone Star was buying gas for seasonal purposes. Well, you can't afford to drill gas wells if you're going to shut them in for 6 months of the year, so George went out and talked to Natural Gas Pipeline and made an agreement with them whereby they would take his gas year-round and they would give him a slightly better price than what was the going price at the time. He got 13 cents an MCF, and he thought he was really doing good, and he was at the time. During this time period, he put together about 350 to 400,000 acres within this outline. And that was for a stratigraphic trap in the Pennsylvania Atoka conglomerates. And at the time he was doing this, I don't believe he realized that he was starting his quest to prove the Barnett Shale. What he was trying to do was build gas reserves and build a company, and that's what he did. One of the provisions in the natural gas pipeline contract was that the gas had to be pipelined usable, which meant that if it was overly rich, you had to strip the liquids out of it. So one of the things George did was build a big gas plant in Wise County, and that gas plant then would strip the liquids out of the gas, and then the gas would be sold to natural gas pipeline, and they would move it to Chicago. So he began if you want to say, about the 40-year journey for the Barnett in the early 50s. And he did it by picking up acreage, by making a contract with natural gas pipeline, putting in a gas plant, building infrastructure through natural gas pipeline, building a professional team to evaluate these things, and then moving ahead. And so he started that. It doesn't mean that other people didn't contribute to what went on in the Barnett. They did. But Mr. Mitchell put all the parts together and made it work. And I don't believe there was anybody else in the country that was in a position to do that. In 1982, which was about a little after I got there, George had asked that we evaluate the remaining potential in the shallow Atoka conglomerates. And we did an analysis, and basically we could tell that the Atoka conglomerates were on the decline, and we did a study that said we had about 10 years left where we could drill enough wells every year to replace produced reserves, build our reserve base, and keep the plant full for stripping gas. And basically, after we did that, Mr. Mitchell said, fine, this is your charge. You are to go out there and preferably within this North Texas area, find a replacement for the Atoka conglomerates. And in a very nice way, he let us know that if we didn't think we were up to the challenge, he felt he could find other people who would be. And we tried to let him know that, yes, we think we're up to the challenge. And whenever he thought maybe we were dragging a little bit, he would come around and kick us in the appropriate area. For a lot of you, you may not be overly familiar with what shales are, but the next few slides I'm going to show are pictures of Barnett Shale. And if you've gone to school like all of us have, you will notice a similarity between this and the black slate that was used on chalkboards. Black slate is a metamorphic sedimentary rock that has had all of the porosity eliminated and all of the usable hydrogen eliminated. The Barnett looks just like that black slate, except that it still has about 4.5 to 5.5% porosity. And in the subsurface, it has a lot of stored gas, and that gas is under high pressure. When we first started, what we were trying to do was use a model that existed in the 1970s and 80s, and that was going after fractured shales, where the fractures were open and capable of storing gas. The Department of Energy and Gas Research Institute had done a lot of work on shales in Appalachia, and the model at that time was that you look for natural fractures. You look for swarms of natural fractures. So that's where we started. And these three pieces of core that I show here show natural. You can see those fractures. The only problem is those fractures are completely healed with white calcite. There is not any open space in there to store gas. Next slide shows two fractures. One's a regional and one's a structural, and they're both healed. And then the next slide shows one that's almost impossible to see, but it's healed. So we started drilling and taking cores, and we were finding all of our fractures healed, but we said, well, we've got to have open fractures out there somewhere. So we said, what we need to do is we need to start fracking these wells and tie into the fractures. And so we began by taking these deepenings into the Barnett, and we would set pipe through the Barnett, we'd perforate, and we would try different size fracture treatments. And this shows 4 wells where we went from a fracture treatment of a theoretical half length of 125 feet up to 250 to 500. I think this is 750 and this 1,500. And what we found was that as we increased the size of the frac, we increased the size of the initial rate. And when you look at this, you can see here at 125, we got 127 MCF a day. We went to 250, we got 273. We went to 500, 527, 750, 837, and 1,500, a million a day. Well, when you look at that, you say, well, that's pretty simple. The problem was this was not repeatable. We could do this in areas, but we only found one area early on where it was repeatable, and that was this area right here. Outside of that area, we could frack wells through here, and some of them were okay and some of them weren't. Well, the problem with an unconventional gas source like this is that you need about a 95% success rate in order to make it commercial, because the economics, particularly at the time we were doing this, even with our elevated price for gas, the economics were good, but they weren't great. And so within this area, we had repeatable results. Outside of it, we didn't. Well, from the period of about 1986 to about 1993, we were able to expand our area of understanding by going in and tweaking our stimulation. So within this area of Wise County right here, we had 5 different tweaks. We did 5 different things to make it work. Then when we moved out into Denton County here, we did a number of other tweaks. And then when we moved into these 3 areas around 2000, we were approaching it from an entirely different standpoint, which I'll show you in just a minute. In 1995, George Mitchell decided to allow natural gas pipeline to buy us out of our contract. And when they did that, basically our gas price was going to go from about $3.25 an MCF to $1.75. And this is one of the times when I questioned his vision, which was stupid, but I did. And within 2 years, it was very clear what he was trying to do. George Mitchell realizes that when people were comfortable, and I'm guilty of this, you don't try as hard to make things work better. And we were not working hard enough to get the cost of our wells down and to get the reserves per well up. He understood that, and he knew that we needed a little bit of nudging, so he did that. And I thank him for that. These are wells that were fracked with water fracks. Prior to using water fracks, we were using gel fracks, and gel fracks were costing us initially $500,000 per well for a 1,500-foot half frac length frac, which was what we had kind of decided on in the Barnett. So we were looking at $500,000 to do that. And after we allowed Natural to buy out the contract, we had to get our cost down or our reserves up. And one of our engineers came up with the idea of using something that UPR was using at Carthage Field, and they called it a slickwater frac, and we ended up calling it a light sand frac. Anybody that comes up with something and modifies it feels like they got to have some ownership of it. So our ownership is it's a light sand frac. Basically, what we did is we eliminated all of the gelling agents and reduced the amount of sand being used, and we cut our fracking costs down to about $85,000. And at the time we did that, we had gotten our gel fracs down to about $385. So you can see there was a significant drop in the cost of the wells. Our initial concern was that while we would drop the cost, we might not increase the reserves. If we dropped the reserves, we felt like by getting a big front-end change in the cost, we could have a positive impact on the well's economics. As it turns out, by going to water fracs, we did substantially better. The reason we think this happened is when we were fracking with gel fracs, we were seeing things like this. If we drilled a well here and we had offsets in every direction around it, when we frack this new well, if we might see that frac in a well here, or a well here, but wells up here would never see it. They wouldn't know that well was there or the frack had happened. When we went to water fracks, we were seeing a very complex structure for our network, our induced network. And if we fracked here, we would hit wells in every direction on the compass. And initially, we thought, oh, damn, that's not good. But it was good. What happened when we would hit these old wells, once we would produce the frack water off of them, they'd come back stronger than they were before. And then the brand new well would produce as good, if not better, than any of the old wells fracked with gel frack. So as a result of that, we said, well, if we can enhance an old well by hitting it with a frack, should we then go in and try to refrack old wells? And that's what we did. And we went into areas where we had fracked these wells with gel fracks. And here's a well, the Mackey, that had been fracked with a 500-foot, and then it was refracked later with another gel frack at 1,500 feet. And then about 1998, we refracked it with a 1,500-foot design water frack. And you can see that that well outperformed either of the previous treatments. And basically, the cost to get that rate was the cost of the refrac, which was almost insignificant. So refracs helped us there. We also found out by using water that we had containment problems in some areas. We had been fracking Barnett in some areas. The fracs were not taking. We weren't getting commercial rates, and we came to realize that what was happening is our frac was going out of zone. And one answer to that was you can double up on a water frac 2 to 3 times and still be significantly cheaper than a gel frac. And so that's what we started doing. This is the discovery well for the Barnett, the CW Slay number 1. And up until 2000, it had produced about 280 million cubic feet of gas. In 2000, we figured out what we had been doing wrong, and our engineers went in there and re-stimulated it, and it came on at 1.4 million a day. This is 18 years later. Came on at 1.4 million a day, and in 50 months it had produced a BCF of gas. And this was in an area where some people had said that the Barnett wasn't any good, had never been any good, and never would be. And what we found was that the Barnett and most shales are good. They just provide technical challenges. When Mitchell, toward the later years, when Mitchell started trying to expand into areas where we had poor containment, we started drilling some horizontals. And we had encouraging results from them. We had mechanical success, but not commercial success. And that was because we didn't understand what to do with the horizontal once we drilled it. We were stimulating them essentially like they were a vertical well, and that wasn't sufficient. Within the Barnett, we used technology that was developed from a lot of different areas. This is a frac map using microseismic frac mapping. It's my understanding that this technology was originally developed to help in the mining industry to help predict when there were going to be failures of the mine shafts. And then it was turned around to some work with GRI and some private companies, and we were able to listen to a frac and pinpoint where we were having rock failure, and then we could map those points of rock failure. We could map them from looking at them from a horizontal plane here and looking in a vertical plane here. That did a lot for us in understanding what was going on in the subsurface. Prior to that, we had no idea what was going on. This gave us a very good idea. One of the other technologies that was very beneficial in the Barnett, but isn't necessarily beneficial in all shales, is 3D seismic. And the reason it was, we found that when you have a lot of structural elements involved in a formation and you have a lot of fracturing, if that fracturing is healed or not, when you frack around that, it can have real negative effects on your well. And so we found out that we needed to shoot 3D seismic, and this is an area of 3D seismic about 15 square miles. And basically what it's showing is the yellow is structural highs, the blue is structural lows, and these are areas of karst where you had caves in the underlying Ellenberger that had collapsed, and the faults from those collapse came up through the Barnett. And they created complications with trying to fracture, stimulate the Barnett. The Barnett is a technology-driven play. Always has been, always will be. This is a plot showing that in a conventional hydrocarbon play, your wells will improve to a point, and then once you get to the maximum desirable limits of that reservoir, the quality of your wells will tend to start dropping off. You can see that over time, we had good wells and bad wells, but over time, the quality of our wells continued to increase. And then in 2003, when Devon, after merging with Mitchell, Devon started doing a lot of horizontals. The quality of the wells jumped up significantly. Horizontals were critical. We had experimented with them, but we had not actually experimented with how to stimulate them. We had tested it, but we had not done anything beyond that. Devon took the horizontal and then figured out how is the best way to stimulate them. And if this chart stops about 06, if we were to continue that on out, you'd still see that we were having increased efficiency as we go on. One of the things in this meeting that y'all going to be talking about is nanoscale features. And this is very interesting. I mentioned to y'all earlier that we knew the Barnett had about 4.5 to 5.5% porosity. The problem was we couldn't find it. We could not see it. We knew it was there because of other tests we did, but we didn't know where it was. In 2006, the Bureau of Economic Geology out of Austin started experimenting with Barnett cores and trying to come up with a process where you could cut a clean enough surface on the rock fragment to look at it in nanoscale technology. And basically, this is a thin section showing a Barnett and these dark areas or the organic carbon within the Barnett. This is the nanoscale picture of the organic carbon, and these are nanopores. And those nanopores are connected by way of nanopore throats, and we therefore have nanoperm in this rock. For years, we didn't quite understand how 4.5 to 5% porosity could have any connectivity. And so we explained the moving of the gas to the fracture and into the wellbore due to diffusion. Well, once we found out how these pores laid in the rock and learned about the pore throats, we had a better understanding then of what was allowing these shales to produce, even if you don't have fractures. Mitchell started the Barnett in the southeast corner of Wise County and expanded it into this area and over into Denton. And then industry started getting interested in the early 2000s, and it has been expanded into over 21 counties, covering an area of about 12,000 square miles. If you look at the area we now have a reasonable technology to estimate gas in place. It's not correct, but we think it's close. And there's a lot of us that believe that for every square mile in the Barnett, we have about an average of 100 BCF of gas in place per square mile. And if you assume you can get 10% of that out, you could get 50 TCF. You'd have 500 TCF gas in place, 50 TCF recoverable at 10%. If you could get that to 20%, then that's 100 TCF. So understanding this rock and being able to increase the recovery efficiency is critical for making these shales work better. As a result of what George Mitchell did, the technology has moved to other source rocks, and the lessons learned in the Barnett were very usable in these other source rocks, but you couldn't necessarily just take a technique and move it to another shale. In the Barnett, we were able to go from about the year 2000. You can see about where we were on the gas, about 150 BCF, and then up here at 2010, on a yearly basis, we were at 1,800 BCF for the year. That is a significant increase, and that gas has helped our country a lot toward supplying the needed energy. But the real value of the Barnett isn't that gas. The value is that basically the Barnett Shale became our class, the Shale 101 of understanding source rocks. And because of what George Mitchell did, we now have a much better understanding. And I was telling Steve Holditch earlier, in the early 1980s, I was very concerned. I felt like there was enough energy in the United States that I could live out my life, but I did not think there was enough for my kids or grandkids. Now I have no concern for my kids or grandkids' energy. We have a tremendous amount of gas. Now the recovery of that gas is price dependent. If price drops to $1 an MCF, it will shut down every shale play in the country. But it won't stay at $1 an MCF if it goes down there. I really will be surprised if it drops below $2. But basically, it is price dependent. But right now, even at $3, gas is a very good buy on energy requirements. This gives you an idea of where the shale plays were able to move. This is the Barnett Shale, the Eagleford Shale, and the Haynesville Shale. Then there's some shales being looked at out in the Permian Basin. But in Texas alone, we have 3 big plays going on. Up in Appalachia, you've got the Devonian shales. The Devonian shale play will probably be 3 to 4 times the size of the Barnett. And the Barnett is huge. In addition to that, we've got the Woodford and the Cana Woodford in Oklahoma. Then we have a number of oil plays in source rocks, and the oil plays have evolved using technology that came from the Barnett. So what George Mitchell did, and George Mitchell deserves the credit, there were people that wanted to sell North Texas, wanted to shut down what we were doing, and George Mitchell reminded them that while there were a lot of voting people in the company, his vote was the one that counted. In addition to the United States, we've seen a huge impact on the world. Up until 10 years ago, Western Europe was pretty much locked in to Russia for their gas. And they were about to have a stranglehold. And we saw this during the early 2000s where Russia was cutting off pipelines. Now we've found that we've got shale gas all over the world. And a lot of different countries can be energy independent without having to go to blackmailing countries to get our fuel. I want to thank Republic Energy for allowing me to do this. Brad Curtis and Emily Connor worked with me on this to help me get it all done. And I want to thank George Mitchell for not firing me several times when he probably should have. Thank you. I almost forgot. I think I'm supposed to take questions. Are there any questions? Yes. Can you come to the microphone? My hearing's not good.
I'm not sure if you can answer this question in any case. We live in San Antonio, and the Eagle Ford
Yes.
Shale has
Yes.
been quite a big event in our area. How does that compare to the Dallas-Fort Worth area?
The Eagle Ford Shale is probably going to be ultimately as big from an oil and gas standpoint as the Barnett gas. The Eagle Ford has better porosity, better permeability. And right now, the main emphasis on the Eagle Ford is basically to the southwest of the San Marcos Arch. But we know, scientists know that we have a tremendous amount of oil in the Eagle Ford to the east of the San Marcos Arch. The problem is that the geologic circumstances there make it more difficult to try and go in, drill the wells, and complete them. I've told people I have faith in mankind. If there's a dollar to be made, we'll overcome the problems. And I believe that the Eagle Ford will end up, through the oil and gas, will end up being substantially larger than the Barnett. And the Barnett is big, but I think the Eagle Ford will be larger. The Haynesville play up in East Texas is large. It's got a lot of reserves. And it actually surpassed the Barnett in daily production, I think, this year. But I'm not sure that on the long haul, I think it may be more of a tie with the Barnett. It may be a little better, but more of a tie with it.
She's next.
Oh, I'm sorry.
I understand that fracking uses a lot of water, and in the state of Texas, water is currently a big problem. Could you comment on how the supply of water will keep up with the need?
Comment on what? I'm sorry, I'm not hearing.
On the, how will the supply?
On water? On water? I'm sorry. I wear hearing aids, but they don't necessarily help. The water issues have really come to the forefront since industry moved into Appalachia. As long as we were fracking in Texas, people didn't care. But once we moved into the eastern area, then people got concerned. And with regard to water, we are using a lot of fresh water, but this concern over contamination of our surface waters is not, in my opinion, a legitimate concern. We are fracking in the subsurface generally below 5,000 feet. Our fracks do not come up shallow enough to get into the water tables. And if there is a problem, it may be in flowing a well back and then allowing water to get on the ground or get into a stream, in which case we have to take action to correct that, and we do. The operators do that.
You didn't answer the question. It's more about the supply of water, not just drinking water, but then water that you yourself need.
Oh, the volumes of water, yes. When we first started at the Barnett in the Fort Worth Basin, we were concerned about the volumes, and we started looking at some of the other industries. And at that time, the industry was not as active then as it is now, but our volume of water was not near as great as the volume of several other industries in the basin. Now, that doesn't change the fact that now we're using more. One of the things that industry is looking at is reclaiming water, and also we're looking at the possibility of being able to frack with salt waters. The reason we haven't done that to date, there's kind of two reasons. One is that all of the chemical additives that we come up with for fracking work in low chloride fluids. And the other is that when you have a lot of salt water and a lot of salt dissolved, your total dissolved solids is greater, and therefore we're afraid that might leave additional residue in the formation. But I believe that we will come to a time when we will be using salt water. We will produce salt water, frack with it, and then re-inject it down into the subsurface. And we will reduce our need to use as much fresh water. I think that the industry is looking at all of these things, and I think we will get better about it. I'm sorry I didn't answer your question first
Dan,
off.
I have a question.
Two more questions,
Yeah, my question is, what's the oil potential of Texas shale formations or even U.S. shale formations? And then how does that compare to the tar sands up in Canada?
How does it compare to what?
Tar sands.
Tar sands. Oh, there is a tremendous amount of potential for oil when you have a source rock that has better porosity than what the Barnett does. The Barnett oil window works a little bit, but it requires some amount of natural fracturing. And we find that there is open natural fracturing in the oil window. There wasn't in the gas window, and there's reasons for that. But in the oil window, there wasn't. And we can make oil wells in the Barnett, but we can't recover much of the oil. In the Bakken and in the Eagle Ford, there is a carbonate member associated with the source rock, and that carbonate member has significantly better porosity and permeability. And we learned about this by way of the nanopore evaluation. We didn't know that existed prior to that.
Okay, one more.
Yes. Could you quantify the economic impact of horizontal drilling, especially when you move offshore shale?
Okay, classify.
The economic impact of horizontal drilling.
Okay. Yeah, horizontal drilling has changed everything for us. When the Barnett is a source rock, and within the Fort Worth Basin, in addition to the source rock, we have migratory paths for hydrocarbons and we have reservoirs. And industry is now using horizontals to develop the migratory paths for the hydrocarbons. We're drilling in rocks that would normally not give up enough oil to be commercial. We're using horizontals to tie a lot of fracture networks together and produce tremendous amount of oil. So horizontals have been critical to what is going on today. In fact, in Appalachia for the Marcellus Shale, which I said earlier was going to be bigger than the Barnett, vertical wells would not work in the Marcellus. It would not work at all. It was tried. It wasn't until we understood how to go after it with horizontals that the Marcellus not only is better, it's bigger than the Barnett. So horizontals have opened up tremendous volumes of oil and gas to us as a country and as a world.
Okay, thank you very much.
Thank you.